Welcome back, everybody. I hope you have had a lovely lunch break and are ready to sit down and listen to some more great presenters for today. So my name is Janet Stacey. For those who don't know me, I work at NZRSE and I am the chair of this session. Following on from the great first session that we've had, we next up have Hilary Oliver from NZRSE, who's going to give us a demonstration of the recent updates of the Silk workflow language. So,
thank you, Janet. Hi everyone. I've been stuck at home sick for a week, and from the inside my voice sounds pretty weird, but hopefully you can understand me. I'm going to give a few slides and then a quick demonstration of new things on the Silk workflow orchestration system. So for those who don't know, Silk is a general purpose application workflow engine with a particular gift for cycling, which is where the word Silk comes from. Many workflow managers run directed acyclic graphs or DAGs. Silk also does cycling ones, but in a very special way that allows it to completely ignore any barrier between cycles. There's no global cycle loop. So if you have any kind of cycling repetitive or iterative workflow needs, Silk is really still the only system in the world can do it properly. One other detail, Silk is dependency based, so you specify a graph of how tasks depend on one another. That's the most flexible workflow paradigm. Anyway, let's get into the presentation. First, I was the guy who commented on this earlier. I do think it's interesting that AI seems to be so good at making pictures of its future plans like this. Anyway, back to reality. So that was kind of a joke, but I can't tell if anyone's laughing, so hopefully it worked. 2 years ago, it was my last NZRSE Silk presentation. Alex Pletzer and I kind of tag teamed it, and we talked about how to run Silk on NZRSE platforms and concentrated on the easy stuff, how to get started with it. This time I'm going to briefly show a Hello World example, then goes straight up to something. I'm actually going to skip the scaling up stuff and go straight to the final demo, which I've outrageously called the magic. So I'll explain what that's about really. And so one interesting thing about Silk is that it has to support production weather forecasting workflows, which are some of the most notoriously complex workflows, never ending, and they run by non-expert operators. So that brings a bunch of features to Silk that actually trickle down some serious benefits to individuals and research users too. I'll try and demonstrate something of that nature. Right. Silk website, silk.org, recently revamped. Take a look. That's your launching point for documentation and support. Shows a bunch of places that use Silk around the world. It is an open source project on GitHub. Originated in New Zealand at NZRSE. If you want to get involved in a challenging and fun project, that would be awesome. Reach out. We've got increasingly good online documentation and a public forum, an online forum, silk.discourse.group, where you can interact with others and ask questions. How easy is Silk 8 to get started? Very easy. You just install it from Conda Forge, and within a minute or two, you can be running simple local workflows, just like that. But you can scale up if you want. Our biggest site is the UK Met Office. Their 2023 status report. They run 10 million huge HPC jobs, and some smaller, but many, many very, very large, expensive jobs per month. 99.6% of those are managed by Silk. Many of their workflows look kind of like this. This is a global forecasting workflow, And that's the full view of one forecast cycle of it. It actually goes on forever. So if you need to scale up, Silk can do it. That's the point of that. Right, I'm going to, whoops, apologies. I was meant to signal that I was going to go into my demo now, but you're going to see a few little messy screen changes like this. Right, I've changed to my terminal application. Hopefully everyone's seeing that. And hopefully I can figure out why it's not working. Oh, man. Demos always go wrong. There we go. We're back. Oh, that one's not back. Okay, I'm going to get rid of this tab. Right. Let's check I've got access to Silk now that I messed that up. Okay. I'm going to switch into a workflow source directory called Silk source NZRSE hello. And what have I got in there? A bin directory with one application called hello.py, and that just simply prints hello world. And here's my hello world workflow configuration. Actually, I've made it slightly more complicated than hello world to illustrate a point, because a single task is not really a workflow. So this runs once a small graph consisting of a task called hello and a task called goodbye. The task called hello runs this application hello.py, and the task called goodbye has some inline scripting it's going to run. So, and actually I'm going to remove that sleep and illustrate something else that I'm not going to go into. Now, how do I run this? Well, I can simply install it and then play it. So install. What that did was copied all my source files to a run directory under home Silk run. And it looks like that. Now I can play it with Silk play. I give the name of the workflow that I installed, and it demonized. It's now running. It's probably finished already because it's so short. So I'm going to run it again in shortcut form, Silk VIP, which is short for validate, which validates the configuration, installs it and plays it. And I'll go in node attach mode. So all the output comes out in the terminal. And here you can see the scheduler log showing in real time how the task hello went through some state transitions. Whoops, sorry. From waiting through queued to submitted as a background job, which is the default, to running. Now, if I wanted, I could easily make these tasks run on other platforms. I'm not going to show you that today. If I show you the workflow installation directory now, you can see the job logs have been captured there. Job.out and job.error, standard out and standard error, and some other information, and the scheduler log. So you can go look at those on disk, or you could just use the Silk log command to look at them. NZRSE hello. And that's the scheduler log. And if I wanted to look at the standard out for the task called hello, there it is there, and you can see it's printed hello world. So that's really the simplest level of a Silk workflow. Now, because I don't have very much time, I've abandoned the middle part of my demo, which was to show how easy it is to scale up from small graphs to big ones as your needs evolve. We're just going to go straight to, I said what I've outrageously called the magic. So that is, this is to do with running these production workflows. I think Silk is interesting that it's why is it so easy to run as an individual? It's because unlike other production workflow managers, it's a decentralized system. There is no central workflow server that you have to install and configure and manage for all users. But at the same time, we have to run these big production workflows. So what I've done here is contrived a little example that is going to illustrate something of that. Now I've taken out the task definitions into an include file, And this might look a bit obscure because there's some Ginger 2 templating language in here, which is a bit Python-like, or very Python-like, I should say. In fact, you can import Python directly into Silk workflow configurations via Ginger 2. And that allows you to programmatically generate a workflow. And what I've done here is I've got a model task, which is generating 3 file outputs, which are being post-processed by separate tasks, and then goes into product generation. And something special is going on in the second cycle. That notation is, I don't have time to explain it, but this is a very powerful notation for making a pattern that describes a potentially ongoing infinite workflow composed of repeating tasks. And if you want to see what it looks like processed out, if you will, in its final form, it looks like that. So this is still this is a runnable workflow. All the tasks exist here. They don't do anything except run this script dummy.sh, which is fine for demo purposes. Here's the workflow graph with the file outputs explicitly shown. Now, to illustrate the scenario, I've graphed this with the Silk graph command, which you can do, but I've annotated the graphs to show. So this is what that workflow graph looks like. The model task depends on its own previous instance. This is showing 4 cycles. Each task generates 3 files, and there are 3 post-processing tasks. Each model does, sorry. And in cycle 2, something special happens. There's this check task which feeds into the post A task. All right. Now imagine this. We're running this workflow. The blue task represents stuff that's already run and succeeded. And here's a red one. In the third cycle, our model application failed. And on investigation, we've discovered that the reason it failed is actually because of some corrupt data on disk that also affected the second cycle, our results, without causing any task failures. These are expensive, long-running tasks, and we don't want to have to restart everything from scratch. So in Silk, what I can do is go back and trigger a new flow that retraverses this part of the graph that needs to be redone because of the corrupt data, and also flows on into the future and will merge with our failed task here, and will carry on as if nothing had happened. And that's all within the same running workflow. In this particular example, I used a task failure to cause a stall, so it's easier to see what happens when I run it. But there could be other parts of the workflow, if this is a real one, ongoing while we're doing this surgery on an earlier task, on an earlier, subgraph. So here's what I'm going to do. I'm going to trigger this task called model at the second cycle, and it's going to flow on with these green dots. They're meant to represent succeeded tasks. And just to illustrate a complication here, you'll notice that check 2 is not downstream from model 2 in this new flow. So this is sort of an off-flow prerequisite, which we have to satisfy. We have to tell Silk that it's satisfied in this flow in order to not cause a stall here. So we have to do 2 things. We've got to trigger this task, and we've got to set an off-flow prerequisite, and then it's going to retraverse this part of the graph in real time and carry on after that as if nothing had happened, saving the day. And that illustrates the final result we're looking for. And now I think I've got about 3 minutes left, which hopefully is enough to just actually show it running. So I'm going to go Silk VIP node attach. I'm now running this workflow to show you how I can view it. One thing I can do is use the amazing Silk TUI terminal UI application. What was that one called? Magic. And this is essentially a GUI that runs in a terminal, and you can do all sorts of things. You can see the different tasks running there, different cycle points on the left. I can drill down to job details, model task, where it's running, what its job ID is, start time, finish time, and so forth. I can view job logs. Boom. I can even view the scheduler log if I go back up to the top level. Scheduler log. Oops, that didn't work. I pushed the wrong button. Clean instead of log, that doesn't matter. Okay, but let's go to the GUI now. So I'm going to type Silk GUI, start up the web UI. And on the left here, I've got all my installed workflows. One of them is running. I'm going to click on that. I could filter out the stuff I'm not interested in there, perhaps. Running. 2 minutes left, I've been told. Right, this is my time. So this is the state I illustrated before, when we have the third model task failed and a bunch of stuff succeeded. I'm going to add the graph view in our UI to get a better understanding of what's going on. I can arrange my tabs how I like. And I'm going to expand the window around the active tasks in this graph so we can see more of it. And here you can see our failed model in cycle 3. And like I said, we want to re-trigger model 2, and we want to set the offlow prerequisite on this task to enable everything to continue again. So I'm going to do the set thing first. I'm going to start a new flow called 2. Now, don't worry, you're not going to understand everything I'm doing here. The point is, conceptually, it ought to be understandable. And so I'm setting on this task post a prerequisite on the check 2 task and saying that that's good to go. So I've done that. Now I can trigger model 2 and everything's going to flow on. Trigger a new flow called 2 at that task. And you'll see model 2 in cycle 2 is now submitted a second job. You can see that in this view here as well. And after that, these are little radial progress bars you can see around the tasks. You can see that the new flow is retraversing that subgraph that we already traversed, and it's flowed on into the next cycle and rerun that failed task again, and this time it succeeded. And things are flowing on from there. So we've recovered from that runtime disaster that seemed like an almost intractable problem. So the main point I want to get across with that for Silk is need for operational support. Whatever goes wrong at runtime, you have the power to intervene and fix it without having to rerun anything, no matter how bad the problem is. Even if you're pulls the plug out of your supercomputer, you can restart it exactly where you got to, and perform surgery on your workflow in terms of re-triggering tasks, setting prerequisites and outputs, and starting new flows over bits of the graph that have already run. And the problem, boom, I'm going to call that. Hopefully there's a little bit of time for questions left. I'll stop sharing now. Sorry, that was a bit rushed. Yes, can you hear me? Cool. Right. Okay. Well, I've just managed to find the chat question settings, so maybe I can address those myself. What would be the most Silk way to handle a workflow with jobs that may be resubmitted with larger resource requests? For example, simulation that initially requests 10 cores. Well, we've got several ways of handling that sort of thing in Silk. You can configure automatic retries for tasks or groups of tasks, and when they resubmit, they can have different settings. Or you could have optional graph branching based on task failure that might run a branch of the graph that actually diagnoses the reason for the failure. And if it discovers that the upstream task failed because of a lack of insufficient memory, say, then that might be a reason to run a recovery task that runs the same model with more resources. So yes, we can handle that sort of thing. Wes says, hi Wes, Zellage for the win. If people are unfamiliar, it's a terminal multiplexer similar to TMUX. Yes, so that's what you saw me using in my demo there. It is indeed a very cool bit of software. What are the downsides of Silk, or when would you not want to use it? Oh man. There are no downsides, and I would never not want to use it. Actually, that's quite a big question. I mean, there are so many advantages and pluses and minuses to every system. I don't think I really have time to go into it here. But obviously, for some use cases, there may be some downsides. I won't deny that.
Apologies all. My headset decided to die, and even though it was plugged in by USB. So that's the breaks of having live on video, but never mind. Thank you so much, Hilary. If there are any other questions for Hilary, pop them in the chat and he can have a look at them and respond to them directly. But we'll move on now to our next speaker, who is Bushra Anam from the University of Canterbury, who is going to be showing us how data science is helping with material informatics. Don't forget to put your questions into the chat.
Hi, good afternoon, everyone. Thank you, Jenny. I am Bushra from University of Canterbury. I'm working on computational modeling of smart energy materials. Today, my topic is a bit different than the practical demo we have seen just in the previous sections in the previous talk. And today we will be discussing about how data science and material science bring together revolutionize material science and material properties. So let's start with a question. Imagine designing a perfect material for superconductors and topological insulators for quantum computing simply by analyzing data. This isn't just a science fiction, it is real. And it's because of the powerful intersection of data science and material science, which is called materials informatics. Materials informatics is a driving force behind materials innovations in the fields like quantum computing. Materials informatics uses a part of machine learning and big data to revolutionize how we discover, understand, and optimize materials. By integrating computational techniques with experimental data, material informatics enable us to predict material properties, explore new materials, and enhance performance without the traditional trial and error approaches. Material informatics also provides us with a systematic way to analyze large data sets, identify patterns, make informed decisions about material designs and applications. So let's see how material informatics has evolved significantly over the last few decades. Initially, computational methods for simulating material properties were limited by computational power and algorithm complexity, but recent advancements have greatly expanded our capabilities. Today, AI plays a pivotal role in the field. It not only predicts material behavior, but accurately we can identify new materials driven by machine learning, which accelerates the material discovery, optimization, and performance evaluation. Industries from healthcare to aerospace are benefiting from these innovations. Let's see in detail how machine learning in materials works. On the left-hand side of the screen, you can see that we start with the input data that we take from both the experiments and then simulations, which give us the structural information and properties of the materials. We put them into a data and create data sets. And then in the center, you can see various machine learning models. These models process the data to extract meaningful insights. Each model plays an important role in analyzing and interpreting the complex data sets we generate. On the right-hand side of the figure, you can see that what are the key structural classification. Using these large data sets, we can identify and categorize material structures based on. Then it helps us in material designing new materials by predicting their potential properties and applications. And property estimates various properties of materials with aids in understanding and optimizing their performance. So let's see how data science and materials research works together. They use the machine learning and deep learning technologies. Material scientists now use several key techniques to enhance their research. For example, classification. These techniques allow us to categorize materials based on their properties or behavior. For example, we might classify materials into different types based on their mechanical or thermal properties. Second one is the regression. This method is used to predict material properties and understand relationships within data. For example, we can predict how materials strength changes with composition. And similarly, dimensional reduction and then cross-validation. We can validate the results, experimental results, and the theoretical results. Now let's have a look about the different machine learning techniques we use in material science. You already know most of them, and we will discuss in detail the particular ones that are used. For example, supervised learning includes regression analysis and classification models that helps predict material properties and behaviors based on the labeled data. Unsupervised learning, on the other hand, is valuable for grouping smaller, similar materials and reducing dimensionality, means three-dimensional or complex materials. And it also enables methods like random enhanced model performance by combining multiple models to achieve greater accuracy and robustness. Each of these techniques play a crucial role to analyze and optimize material properties. Having discussed various machine learning applications in material science, let's now focus on a specific type of a model, convolution neural networks. They're particularly powerful for image-based materials research. They plays a role in analyzing structural properties, relationships from images of the materials. It appears using different layers like convolution layer. This layer extracts local features from images such as edges or textures. It's crucial for identifying important details within the material image. Pooling layer. This layer reduces the resolution of the image where required, which helps in simplifying the data while we are preserving essential features. And then fully connected layer. This layer combines all the extracted features to make prediction. It generates the information gathering by to provide insights or classify materials. They are highly efficient in processing images of the materials we will see in a case study next, including atomic structures. By analyzing these images, researchers can predict important material properties such as their band gaps that are very important for understanding and designing new materials when we make composite materials. So this is one of the microstructural characterization is one of the applications of CNNs in material science. CNN helps identify correlation between materials microstructure and its mechanical properties, which is very important for improving materials properties for specific applications. We can tailor the materials according to the applications required in a particular field. As we know that microstructures can reveal everything from how the material was processed to its mechanical strength and how it might differ under pressure or under stress. By analyzing images from microscopy, these CNN models automate the interpretation of these complex structures. Here is a image of different microstructures that has been taken from a paper by Wormus, and they have used the culmination CNN network for recognizing the metal alloys. And this image is for the microscopic images of technical casting alloys like cast iron, and then this one is aluminium alloys in different shapes. These images has been identified by the field experts into 7 different categories, and there are sphere, polyhedron, dendrite, needle, petal, wing, and Chinese. Like you can see, there is a very close resemblance between twin and Chinese. But still, these models can identify these precise differences in the images. In this case, we have seen that the particular application of CNN is for alloy microstructure analysis. By using the NELSNUT 201 architecture, researchers achieved over almost like 91% of the accuracy in classifying complex morphological patterns. These models-based approaches surpasses traditionally logic systems, which often struggle with the different structures. Like I have given an example about the closely related microstructures. This solution can be applied with very little manual setup, and it is accessible for the domain experts who may not have machine learning expertise but want to use that in material research. So, after discussing about the how material science we can use materials informatics in revolutionizing material science and discovering new materials, like of course it's an emerging field and there are challenges associated with this field. Material science has undergone a significant evolution over time, transitioning intuition-driven discipline to one grounded in mathematical and computational models. Initially, there were no quantitative methods. Earlier researchers just used their intuitions. However, the development of these models, like those based on thermodynamics, make a major turning point. In the recent years, this rise of computational power had brought us into a new era. It's a big data computing. This enables a simulation using techniques like density functional theory and molecular modeling as a computation simulations, which have become critical in tackling real world challenges. Moreover, modern neural language processing are being utilized to mine materials science literature. For example, one of the researchers like Louis and their colleagues developed systems that extract meaningful descriptions with remarkable accuracy, streamlining the process of materials discovery. Despite this significant progress, there are still major challenges in applying research findings to the real-world material applications, which will often take 15 to 20 years or more. And why? One of the main reasons is the rely on trial and error method, which slow down the transition from research to the practical implementation. This is because the data we work with is large and complex, making material characterization processes both resource intensive and in recent years, feature selection methods have been struck in improving model accuracy. By utilizing the domain knowledge, this technique can improve the accuracy in key material properties like melting point, hardness, and conductivity. And the development of highly performance predicting models will be the key in overcoming the limitations of the current computational and experimental models. allowing us for the rapid and accurate predictions. For what we see for the future of the materials informatics, it's very bright. Future development in machine learning are expected to produce predictive models with unprecedented accuracy. These advantages will allow us to better understand and forecast material properties. We can improve the data integration, creating comprehensive material databases through text mining from scientific literature. It will be a game changer by aggregating valuable data on molecular properties and reaction conditions. We can significantly improve our prediction powers or capabilities. So, machine learning, there is always an innovation in machine learning techniques. Advances in deep learning led to the more efficient and accurate representation of raw data. As we improve our understanding of how neural networks process information, we will see more reliable and acceptable models in the materials informatics. And then again, integrating machine learning with tensor theory, which is one of the best computational model to study material properties, will significantly improve our ability to predict the complex molecular features, and we can study the quantum systems. This will help us solve many problems in computer chemistry and material science. So, what we have seen that the machine learning has just changed the material research by allowing us to analyze complex properties with the predict novel material properties, optimize processes with good precision. This transformation is given by various machine learning techniques. We have discussed about unsupervised, supervised, reinforcement learning, transfer learning, and then deep learning. These methods have been essential for getting new material properties, enhancing their synthesis, and improving our data-driven exploration. However, despite its potential, there are always challenges we must address, including as we have already discussed, like data quality, algorithm complexity, and of course, third one we haven't discussed was the ethical considerations. The future of material research relies on overcoming these obstacles through the continuous innovation and by collaboration. So we have to, these new techniques can continue exploring these learning into our field, so we can drive forward the evaluation of material science, and we can unlock new possibilities for innovation and discovery. Yeah. Thank you. This is all for yesterday, and now I will stop.
Thank you so much, Bushra. That was a really great talk. People, get your questions into live Q&A to ask Bushra while we wait for some. Alex has asked, you said in the future plan section that you are looking at incorporating machine learning and deterministic methods in the future. Is there any short-term movement in that space?
Yes, there's a rapidly emerging, like there's lots of like work going on in the organizing the databases. As good we have the data, because the problem is for some of the materials we don't have that much amount of data, and also the data we have is not 100% reliable. We rely on the scientific publications and extract data from there. So yeah, there are lots of efforts going on to improve the data accuracy. By data accuracy, we can definitely about the materials.
As a follow-on, Alex has also asked, have you considered using a workflow engine like Silk that was just shown to design new materials?
Yes, I have not used it in detail, but yep, it's really a good one. I would suggest from one or two others, it's the a good one. Yep.
Cool. And Maxime asks, are graph neural networks also used? And if so, how do they compare with CNNs that you've got?
They can be used. I don't know about, I haven't come across any paper that are particularly or any research that are particularly using um, graph neural networks because it's like more of using the CNN and other models to just relate the properties and finally, yep. So,
Thank you so much again, Bushra. I'm sure everyone's clapping away in front of their own screens. Keep on getting your questions into the chat for Bushra or for
yep.
Hillary's earlier talk. And if you're looking for answers to your questions, then you can go to the Answered Questions tab to find them, because Hillary has answered some already. Next up, we have Nick Snellgrove from EPU Interactive, who's going to be talking about connecting decision makers with complex models to battle aquatic invasive species. So I'll just welcome Nick onto the stage and get those questions in while his talk's going.
Awesome. Thanks for that. Kia ora, everyone. My name's Nick. I'm a tech lead at EPU Interactive, and what I want to cover today is looking into one of our Shiny applications which we've used for the purpose mentioned in the title there. Hopefully this will provide a bit of inspiration for improving the accessibility of these complex models and helping support decision makers out in the field. Before we get into that, this project and this talk wouldn't be possible without our collaborators at the University of Minnesota, the Aquatic Invasive Species Research Center. So a special call out to Nick Phelps, Amy Kinsley, and Alex Badges for all their support over the years, and also to my own colleagues at EPU Interactive who have helped to work on this project as well. So the topic of this talk today takes us to Minnesota, which is the land of 10,000 lakes, is what they put on the marketing. The actual number is around 11,842 lakes. And from those, around 8% of these are infested with some kind of invasive species. This is actually only a small part of the problem as well, because they are actually more like 18 to 24,000 uniquely registered water bodies within the state, whereas they only have detailed inspection data for around 9,000 of those. So for local authorities, decision makers, county managers who are trying to combat the spread of invasive species, it's a big problem because there's a lot of complex sort of networks between different lakes, through rivers, boater movements, things like that, and a lot of different species to contend against. This is critically important for Minnesota, and I think in a way, as a New Zealander, you can kind of empathize with this because for them, the lakes are kind of hugely important for the social fabric of the state. It's the lifeblood of their state. And so coming from New Zealand, where we also have that focus on protecting our native ecosystems with critical importance, I think we can really kind of empathize with what they're going through. For this talk, we're going to be focusing on a few different species. So we have from the top left, zebra mussels, starry stonewort, Eurasian water milfoil, and spiny water flea. Now, as far as I know, none of these species are currently present in New Zealand, but these are a significant issue within Minnesota, which is why they were focused on by these researchers at UMN. Funnily enough, actually one of the other species not covered in this talk, but monitored by their DNR, is the New Zealand mud snail. So in some way, we do actually have a stake in this data, whether we knew it or not. So to combat the spread of these species, the researchers from UMN approached us to help develop the AIS Explorer, which is what we're going to find out about now. So the goal with the AIS Explorer is to provide a decision support and a risk management tool for county managers and decision makers on the ground in the state. As I mentioned, the lakes are very important to the tourism and sort of the social fabric of the state. So preventing the spread of these species to lakes where they haven't become established yet is really important. There's a lot of complex analytics and models which have been developed to that end, but the complexity is a little bit of a barrier. Some research papers can be quite difficult to interpret and share with the end user. So we want to kind of open up that door and make this stuff more available to decision makers so they can easily use the research to figure out what needs to happen. Also supporting that with things like webinars, training, and support tools like what we see here. So the AIS Explorer is incorporating 4 different models. We started off initially with a risk model and an inspection model. And then over time, as the AIS Explorer has been expanded and updated, we've added 2 more models, one for interventions and one for collaborations. So a little bit of a summary about these models here. I'm trained as a software engineer. I can't speak to the inner workings of these models myself, but I can give a quick summary. So the risk model is covering the infestation risk for lakes over the next sort of 5 to 8 year period. And that's using inputs based on boater movements, water connectivity, things like habitat suitability for different species, the size of lakes. There's all sorts of different information going into this model, alongside where infestations are currently established for different species. The inspection model prioritizes the placement of watercraft inspectors to maximize the effectiveness of inspection efforts within a single county. The intervention model kind of allows users to create like a customized report, which allows them to say, if I was to perform these sort of interventions, so inspecting boats, decontaminating, hot water washing, education and outreach, how does that change the risk of infestation for certain lakes? And then the collaboration model provides kind of collaboration networks between multiple counties for placement of watercraft inspectors. So if they pull their resources together, how can they optimize the placement of inspectors to capture the most risky boater movements? So these are the 4 models which are going into the AIS Explorer. And they're built up in a mixture of R and Python kind of code in the background. There's some significant challenges that we had to overcome for this. The source data which goes into it updates pretty frequently. So as the source data, we're using the infested waters list from the Minnesota DNR. And during the winter, that doesn't update very often at all. But during the summer, this can be updating on sort of a weekly basis. These models that are going into the app are also quite complex. For the risk model in particular, this is a model which takes days to run, which I guess in the scheme of things, it could be a lot more complex. It could be larger, but it's nothing to be sniffed at. So we need to find a way of combining these things together and presenting it in a reasonable time frame. As already mentioned earlier, getting access to the results of research can be challenging. So we wanted to present this information in a way that it's readily available for stakeholders without having to dive into a research paper and figure it all out by reading. And then I guess lastly, the manual updates. So if we were to go in and say manually run a pipeline once a week, that's not really a practical process. That requires a lot of sort of manual intervention and sitting around waiting for things to happen. So all of that came together in September 2020 for the first version of the AIS Explorer. So this was all built up using RShiny, which is open source application platform, and built on an AWS cloud infrastructure. So this is, since it was released and ongoing, used by county and lake managers, decision makers, researchers, and more throughout the state of Minnesota, and actually beyond, as we'll get to a bit later. So that is freely available. If you go to that link, aisexplorer.umn.edu, you'll be able to take a look at that as well. So I want to give a bit of a demo of how we've connected these models up into our application interface, starting off with the risk model. So you can see here that as we go in, we have a map which comes up, which shows us the risk of lakes becoming infested within the next 5 to 8 years. We have pop-ups which show more information about specific lakes, and then we have filters down the side controlling things like which species we're looking at, which risk scores we want to consider, what locations we're looking at on the map. including also layers. So we can enable or disable things like location boundaries or names or risk score or limit connections. We can go onto a specific lake and then show the incoming and outgoing connections for that lake, meaning that we can see where infested traffic is coming from or going to in an alternate view of that. You can also see here in a moment, you can see here on the video now, we can have multiple counties considered at the same time. And recently added is an expansion to Wisconsin. So this is still kind of under development in terms of the research, but instead of just being for Minnesota, this model is now expanding to also provide estimates for Wisconsin lakes as well. So that's a bit of an overview of the risk model. So moving on then to the prioritization for watercraft inspections. So this was our other sort of original model. And what this is doing here is prioritizing placement of inspectors at lakes within a single county, maximizing the effectiveness and coverage of risky boat movements. There is some sort of simplification going here. It's sort of representing a best case scenario. Some of these lakes are quite large, so to get full inspection coverage, you would probably have to be quite aggressive, but you can see that you can customize like which species you want to inspect against. You can customize for whether lake should be excluded from the model output. So say in this example, Mill Lacs, perhaps there's not a boat ramp or access to the lake within this county, and then you can rerun the model to get those results through. And you can see a ranked list of where you should place your inspectors for the optimal effectiveness of your inspections. The map and the chart on the right are showing the same information as we see in the table there. So the map shows you which lakes you would need to place inspectors at, while the chart shows you this kind of diminishing returns of how many boats are being inspected versus how many inspection stations you have set up. This will also come back to this in a moment because this model is sort of foundational for the collaboration tab, which we'll see shortly. One of our recent additions here is the intervention impact tab. Now, this is a heavily user-driven model, which has kind of three main parts to it. So we created like a user login system where people can sign up and save their results from previous reports, get a summary of their settings and things like that. Creating a scenario, you can pick which lakes you would want to intervene at from one or multiple counties. So you build up sort of a list of focal lakes. And then from that, you can then set an effort level, which we have some defaults in place based on how many boats would be inspected. You can also set an effectiveness level, which is then saying if you apply some intervention, how many boat movements would be made unrisky. So default set to 50% for watercraft inspections as an example. And then we also see the cost of different interventions. So these are estimates from a state level, but it gets you an idea of if you were intervening at a certain scale, how much is that actually going to cost? And all of this comes together and is submitted to a separate server, which does the processing of this model. As I mentioned, it's very heavily user-driven. The model takes about 10 minutes to run in this case, but we don't want to have people sitting there waiting 10 minutes for a model to complete. So what we do instead is we send them, email out a report. This report is also saved to AWS S3 and available through that login platform. And this report contains kind of the completed model outputs from the interventions that they picked. So you can see it summarizes the cost. You can see how the forecasted change in risk plans out for your interventions. You can also see a little bit further down in this video, you'll be able to see a comparison between the status quo and your intervention scenario. So to see how many or what effect your interventions have had on new infestations within your selection. So by sending this out as a report, people can kind of compare and contrast multiple different intervention scenarios without needing to run the model and then sort of keep bouncing back and forth. You can just kind of save that away, share it around. You can save it as a PDF, share that around to whoever needs it. So really making that a very heavily user-driven model. And the last one to look at here is the collaboration model, which is based on the watercraft inspections, but instead of looking at a single county, it's instead looking at counties within a collaboration network. So we have some pre-processing which creates these collaboration networks. So that's different counties in groupings of, I think, less than or equal to 6 counties together. And so you can see that on display at the top there. You can see which counties are selected or connected to each other in this network. You can see how the lakes are connected to each other within that collaboration group. And then you can see a group planning view, which says, if you consider all of these counties together, then where would you prioritize placement of inspectors as across that whole group? You can also see in this paired planning view here that you can compare individual counties with each other. So you can say, if I wanted to prioritize inspections in Hennepin and Cass counties, here is how I would do it. Prioritize Minnetonka first, Independence and Medicine in Hennepin County, and then in Cass County, you'd be looking at Leech Lake, Gull Lake, and Woman Lake. So very similar foundation as the inspection model, but it's kind of going more towards collaboration and bringing multiple counties together. So the AIS Explorer in its current state has been in continual use by decision makers, county managers, researchers across the state. And we've had the opportunity to kind of add more functionality, add new models to it over the course of its life so far. And this process is continuing. So future updates are planned, including the completion of the Wisconsin data update. So we'll be getting a more robust boater movement network plugged in there, extending also the Wisconsin data into some of the other parts of the app. So the intervention, collaboration, and inspection models, eventually including Wisconsin in there. Potentially in the future, we would look to extend the risk model or intervention models with additional species. Currently, those are just looking at zebra mussel and starry stonewort. So we would expand to also include Eurasian water milfoil and spiny water flea, and then extending the collaboration models with game theory as another idea which is out there. So I guess to close up here, a bit of a whirlwind tour through the app and how we connect those models into kind of a usable, user-friendly interface is that against these invasive species, it is difficult to score wins. Generally, just sort of keep on battling against them rather than remove them outright, especially in such a large and complex network and ecosystem. The AIS Explorer, though, can and does serve as a powerful tool for decision makers in their fight against these invasive species. It connects up these models in an accessible and intuitive manner now and hopefully into the future as well. If you want more information about that, here's some related publications. You can also see those on our website. For examples of other similar pieces of work that we have done, you can also look at our work page on our website. And otherwise, thank you all for listening. If you want to stay in touch or learn more, check out our masterclass series as well, or get in touch with me via email. I love to talk about this, so thank you.
Thanks so much, Nick. That was a really interesting presentation and useful of how New Zealand is affecting the world. We've got a couple of questions in the chat, which we've got a little bit of time for. So the first one is from Alex. You mentioned it may take days to process the data. Do you use or have you considered any strategies to accelerate the processing time, like parallel processing or GPU use?
That's a good question. It's something that often comes to mind for me. Every time we do a round of updates, I'm looking for some way to speed it up. I think the initial version of the processing was basically just one R script, which ran end to end and just dumped everything into an S3 bucket. Now we have a little bit more sophistication going on there. So we have, for example, we have like AWS Lambda functions, which are like only running the pipeline when absolutely necessary, when the input changes. We have separate pipelines in place for Minnesota and Wisconsin. And we did also spec up the instance which is running that code. And for some parts of the models, we are able to parallelize some of that. It's an ongoing process, and we're always looking for ways to improve that. But yeah, in some ways, yes, we have been able to optimize it. In some ways, there's still more we can do.
Another one we have is how did the collaboration with University of Minnesota come about? Was it just through your website, or was there a connection already?
So if anyone was able to catch our director Petra's talk a little bit earlier today, she also talked about another project that we did with UMN. So I think it just kind of came around as sort of networked, like the people that we worked with on this other project just kind of knew the people from MESARC and sort of made the connection that way. But it is quite a long-running collaboration. I think at least 5 years since this project was conceptualized, and the research has been going on for at least another 5 years before that. So it's quite a foundation for it.
Awesome. Wolfgang is asking, how customized are the portal and backend? Can they be easily adapted to other use cases?
So the AIS Explorer interface is very heavily customized. One of my other colleagues, Shana, our design lead, will be giving a talk tomorrow about kind of the design process that we have for dashboards. And typically what we do with that is it's a very sort of collaborative process with the researchers that we're building the application for. So like right from the design phase, it's customized towards their outputs and their needs. The principles that we use are absolutely the same across multiple projects. So like especially the Shiny, application framework, that's our kind of our bread and butter, and that absolutely can be extended for whatever domain you're wanting to build an application for. So
there's no more questions in the chat, but I do have a couple myself.
Sure.
The first one, which would be, do you know if they are monitoring or including the monitoring of these intervention procedures that get chosen through the dashboard in the risk model for future instances?
So I believe the risk model is based on sort of a zero intervention estimate. So the intervention impact tab is more of like a user-driven, I think the target audience for that is more like people within a certain county or within a certain collaboration group to say, if we intervened here, if we set up inspectors here, if we did boat washing here, if we put up posters here, how does that affect things? Whereas the risk model is kind of giving a baseline. If nothing else changes, here is the risk. So
it may deviate from actual risk as time goes by. Okay.
Yeah.
And the other question I had is, you talked about this project being a combined Python and R processes as part of it. Have you considered using Shiny for Python if a lot of the machine learning is in Python?
Yeah. I guess if we were to build it again today, we would definitely consider it. I think Shiny for R was the go-to for us because at the time that's all that was available, and also the researchers at UMN, a lot of them are very comfortable with R, and that's sort of how they were building their models. So a lot of it we were able to just sort of plug in to our Shiny application without too much hassle. That's kind of our typical process. Like we'll try to fit whatever the model is that we're using. We try to fit around that. So
great. Well, there's no more questions that have appeared. If you do think of any in the next little while, please feel free to add them to the live Q&A chat, and Nick can address them as they come in writing. Otherwise, it's time for an afternoon tea break. So go do that toilet break or have the coffee that you need to stay awake for the rest of the sessions. No, you don't need that. And otherwise, we will have you back for the next session that starts at 2:50, I believe. So 20 minutes or almost 15 now for you to go away and do what you need to do.